Okay, let's talk through the mechanics of logistic regression and how we set logistic regression up. So first let's start with the basic setup. And what is logistic regression? You saw from your reading, it is a classification algorithm. So we are going to classify, right? And so the idea is to get an assessment or a forecast based on a feature set, how likely an observation is of one category or another. So in the Titanic data set, the classification is, did the person survive or did they not? And so maybe in an image classification it would be, is it a cat or is it a dog or is it neither, right? And so classifications can be binary, right? And binary are 1 and 0, or they can be multi-class, right? Where they could be 1, 0, 1, 2, 3, whatever the case may be. That's a 3. So in these multi-class cases, you have multiple values. We won't get in the mechanics of them here, but they're very easily extended in the scikit-learn library. Instead, what we're going to do is we're going to focus on the binary case. And how we set the binary case up is through the mechanics of something called log likelihood. So what you see down here is the logarithm. That ln stands for the natural log, and it's a function that you may have used on your calculator in the past, but I'll explain why we use the natural log here in a bit. But you can see that this p is a probability divided by 1 minus the probability. So this probability divided by 1 minus the probability is called odds, right? Which maybe makes sense, right? It's the ratio of the probability. And we're taking the natural log of the odds, so we call it log odds. And then we've expressed the same equation that we've had from our linear regression. The slope times x plus b is equal to this funny looking variable here called theta. You'll hear us refer to this again. Theta is the catch-all variable that refers to this linear combination over here, right? And this linear combination could be large, right? It could be represented in let's do this. It could be represented in a set of weights. So weight 1, x1 plus weight 2, x2 plus b, right, is equal to theta. And these number of x terms and weight terms could be arbitrarily large. But in general, this linear combination is equal to theta. And then what we do is then we rearrange this equation. We rearrange this equation here and we solve for p. Right, so we solve for this using some algebra, and when we solve for p, we get the equation down here. This equation down here is commonly referred to as the sigmoid function. You'll hear that referred to quite a bit. And the sigmoid function has got some really neat characteristics for classification purposes. So it equals p, and p now becomes y hat. And if you remember y being the attempted guess or the prediction of the outcome, and this little hat on top denotes that it's a forecast, right? So it's not a perfect guess, but it's some estimate. The sigmoid function allows us to guess a classification, whether or not y is 0 or 1, with some value in between the range of 0 and 1. And if we were to plot this sigmoid function on a graph, it would look like an S-curve, look like this. Right? And the S-curve's got this characteristic fancy math word called an asymptote, meaning that this line always gets closer and closer. It always gets closer and closer to this top line, and always closer and closer to this bottom line, but it never quite gets there. The center point here is the mean. Right? It's the average of the S-curve, and that'll be important here. We'll talk about it in just a second. But no matter how large of a positive value you put in, it never goes over 1, right? It approaches 1, but it never goes over. This is my attempt at a 1. And then no matter how large the negative value, it never goes less than 0. So I'd encourage you to pause the video right now and try this. So pause this, take the sigmoid function, code it up really quickly in Python, and try to input values for theta. Try to input values for theta that are either really negative or really positive. And you can just see from the structure of this function, right, that like as theta becomes really, really really, really large, this number becomes extremely small, meaning that it approaches 0. And as this number becomes extremely small, this negative value ensures that this explodes, meaning that 1 divided by a really, really big number is close to 0. And as this thing goes to 0, right, as this value goes to 0 up top, as this number gets really large, it gets really close to 1 over 1, right? So you can see that this bound is quite valuable because, when we plug in some linear combination of features, the closer it is to 1, the more likely it is that we're going to classify as something as being positive, and the closer it is to 0, the more likely we're going to classify something as not being positive or as being a false value. All right, so let's talk about the mechanics in terms of the cost function. I've got a scary-looking formula here that you might have seen before if you've done any machine learning. So unlike the sum of squared error, if you remember the sum of squared error that we use for linear regression, right? We did this big sigmoid function, and then we had y hat minus y squared, right? And this squared term gave us a convexity that allows us to use gradient descent to solve for the linear regression component. Unfortunately, in the case if we use this sigmoid function in place of this y hat, it's not convex. I won't prove that to you, but you can trust me. There's lots of proofs online you can go check out. It's not convex. So if we want the function to be convex and take advantage of gradient descent, we need to formulate our loss function like this, where you can see that we've got some interesting things. We've got our y hat values, which are calculated per the sigmoid function, and we're taking the natural log of those. We've got these yi values. These are the realizations or the actual data, and a couple of mechanics we'll walk through, like a quick layout down here in a second. But you can see that if the actual observation is 1, right, then this term will be evaluated. If the actual observation is 0, right, then this term goes to 0, and then this term will be evaluated, right? And so this natural log of y hat, or natural log 1 minus y hat, it basically benefits, it gives a benefit or a penalty as you get closer and closer to the correct answer, right? And so what we're trying to do here is we're summing up all of these error terms associated with how close you are getting to a correctly predicted value. And the mechanics of this are that these natural log components do result in convexity. They are convex. Check. So then we can use our gradient descent algorithm, right, with this derivative, which we won't calculate here with some learning rate. Right? And this becomes the basis for most of the advanced machine learning concepts in the future. Sometimes you'll hear this cost function referred to as cross entropy. And or sigmoid cross entropy or something like that. Basically, the idea is if you were perfect at prediction, this value would be 0. So the goal is to hopefully find a model that gets you as close to 0 as possible. Okay, so down here I've got an example of 4 points in a data set. And let's say that we wanted to calculate the cost of these four points. So this is yi, and this is y hat I, right? So this first value would be 1. So I would use this, this first term here. So it would be 0 times the natural log of 0.3 plus 1 minus 0, so 1 times the natural log of 1 minus 0.3. And then, of course, we would add that down here. And then you can see that this term would go away, and then all I would be left with is this 1 times the natural log of 1 minus 0.3, right? And this would be considered the penalty associated with predicting the incorrect answer. So you'd want that to be, this value to be as low as possible. And this is the idea of entropy, right? Entropy is the reduction of information. And if I do it in kind, on the next one, I have 1 times the natural log of 0.7 plus 0, right? 1 minus 1 times the natural log of 1 minus 0.7, right? And now you can see that this term doesn't carry through, but then we have 1 times the natural log of 0.7. And then if I follow this the rest of the way through, I've got 1 times natural log of 0.8 plus 0 natural log 1 minus 0.8 plus 1 times the natural log of 0.9 plus 0 to natural log of 1 minus 0.9 plus 1 or 0 times the natural log of 0.2 plus 1 is the natural log of 1 minus 0.2. All right, I add all of those things. I take the you can see that there's a negative sign here. That's helpful in the regression. But I add all of these terms up, or the negative value of all of these terms up, and then this gives me, right, a simplification where you can see that I'm only collecting, or I'm only evaluating one side of the term, which is I am evaluating how likely it is that something will guess wrong, right? So these are penalties or costs associated with this calculation. Okay, so that's how we do one iteration of the function, and then we calculate these values, and then we take these values through, and we evaluate gradient descent with some number of iterations, right? And that number of iterations then improves until you've got some function that fits as well to the data as you possibly can, given the constraints of the sigmoid function. Okay, so once you have a trained model, so let's say this is our trained model here, give the S-curve. In a classification problem, you then have a consideration of where you place the decision boundary, right? And so if the sigmoid function is attempting to guess either 0 or 1, this function is continuous, so it can take on any value in between 0 or 1. So what a decision boundary is it's a point, an arbitrary point on your function that you'll draw, where above that point you'll guess 1. Right? And below that point, you'll guess 0. And this has significant impacts on the performance of your machine learning model. So a lot of times what we'll do is you'll see these things called a ROC curve, receiver operator curve. And a ROC curve is some sort of function that looks like this, right? It usually has a curve that looks like this. And the idea with a ROC curve is that you have true positives on one side, how good you are at guessing the correct one, and then you have false positives on the x-axis, or sensitivity. I think this is technically 1 minus the false positives. But the idea is that as I move this blue line up and down, I can put myself at different points on this ROC curve, right? Do I want to get better true positive rates, which means that I'm going to have lower false positive rates, or do I want lower false positive rates, which means I'm going to have lower true positive rates? So most of the times you'll see this decision boundary drawn somewhere in the middle, so you'll pick a point right here on the curve. The best possible ROC curves have a point that's like way back up here where you have no false positives and no true positives, or and all true positives. But that's obviously very, very rare. So as you tune for a specific application, this decision boundary becomes important. For the rest of this class, we're just going to assume a decision boundary of 0.5, which is right in the middle. That's the most common that you'll see, though not always the case. Sometimes your use case requires something else. But it is an important consideration. Okay, I'll see you in the next video where we will implement some of this in code.